Continuing on, let's talk a little bit about acid rain, just what it is. This is a situation in which you have carbon dioxide in the air. You can look at the reaction with H2O. Combine those, it's very easy to see. You can get H2CO3. That is carbonic acid. This is a gas in the air. This is a gas in the air. This can then be a gas in the air. When air condenses with acid, with carbonic acid in it, there's your acid rain. If it's something that that acid has a negative effect on, such as possibly a tree or some other type of vegetation, it will kill it. More to the point of being really detrimental is what's called Sox and Nox, where Sox is SO2 or SO3 and Nox is NO or NO2. I'll illustrate what can happen with those. SO3 can do the same thing and give you H2SO4. We know this is one of Mother Nature's 7 strong acids. And so this is very detrimental to a lot of organisms and materials. So this is basically how acid rain forms. You just kind of need to know it's a real thing, and it's normally combined with some material combining with water to form that acid, which then condenses or falls out with as the rain falls through the atmosphere. It pulls it down and causes problems. Right, let's now move to, in the textbook, what is section 14.3, relative strengths of acids and bases. As a reminder, this is the cube, if you will, that you're supposed to be able to work around with great ease. pH to POH to HO minus to H plus. Those conversions should be standard fare for you. What we're going to do next is do some calculations, and it really helps for you to analyze as you're reading the question what it is exactly that you're doing the calculation, because if you recognize a strong acid from a weak acid from a buffer, then you can cut straight to the chase. You can cut straight to the formulas for those particular species. Otherwise, as you will see in the way most textbooks teach, you have to work through the long RICE process. So, the first thing we're going to do is consider strong acids and strong bases. Of course, you need to know what those are. We've gone over those. Let's see, do I have it on the next slide? Yes, I will go over those in just a second. And then anything that's not a strong acid or a base is necessarily a weak acid or a weak base, respectively. And then finally, we will discuss what a buffer is. Okay. Your 8 strong bases, what are they? They're hydroxides of lithium, sodium, potassium, rubidium, cesium, barium, strontium, calcium. So lithium hydroxide all the way around to calcium hydroxide. Those are your 8 strong bases. Any other base that you see, any other base, you can use the weak base formula. Your 7 strong acids, my little memory jogger here, is to use these touching central atoms here: HI, HBr, HCl, chloric, HClO3, perchloric, HClO4, sulfuric, and nitric. Those are your 7 strong acids. Any other acid can be considered a weak acid. Okay, so the first thing we're going to consider is how to calculate hydrogen ion concentration. Of course, it could ask you for hydrogen ion concentration. It could ask you for hydroxide. It could ask you for pH, or it could ask you for POH. Those are all the same questions. That's how you need to see that. All the same question. Typically, I'm going to illustrate this by either calculating H plus or pH. Right, a strong acid. Here's why that's important to recognize that, because those equations are real stinking easy. So let's look at a RICE for a strong acid. Strong acid, by definition, is something that disassociates 100%. What that means is, if we start out with an initial concentration of acid, and for the rest of this time, I'm going to use the abbreviation Ca for the initial concentration of an acid. This is not in your textbook. This is not most other places. This is something that I got from a professor in UT when I helped tutor one of his students, and he had some fantastic shortcuts. As a matter of fact, these shortcut formulas that I have for you to use, those all came from this guy's notes. And that's how I teach it. It is so impressively easy. Okay, if you like the way the book teaches it, read it, and by all means, do it that way. Right, and not all questions can you use these, but when you can use these 6 formulas, I would strongly encourage you to be able to do that. Right, okay, so let's talk about the calculation of H plus for a strong acid. The thing that is so important here is that it disassociates 100%. Consequently, if you have an initial concentration, every bit of it is used up and this term goes to 0. So essentially there is no Ka. So what is your H plus concentration? Your H plus concentration is just going to be Ca. So it's really easy. If you know what the concentration of the strong acid is, it's going to be the exact same thing that the concentration of the H plus is. Okay, so let's now take one of those questions that may look like that. Right, shortcut formulas. And so as far as the shortcut formulas go, you now know the shortcut formula for H plus concentration for a strong acid is just equal to your initial concentration. And likewise for a strong base, of course, which this is Cb, is going to represent the initial concentration of your strong base. It's just going to equal whatever the hydroxide concentration is. So let's look. Let's look at the pH of a strong acid problem. What is the pH of a 0.05 molar nitric acid solution? Well, immediately you recognize nitric acid as one of your 7 strong acids. And so you immediately say, oh, I know what it is. I know that H plus is equal to the initial concentration, and I know the initial concentration is equal to 0.05. Therefore, H plus concentration of is equal to 0.5. And now you just do the simple conversion of H plus to pH. And once you're asked that, you're on home territory because you now know fluently how to go from H plus to pH. You know that. Right. That's going to come up over and over. Please, please, please get fluent with that. Let's go to the next one. Okay. The next is weak acid. And this is a little bit hairier. So let me walk you through this, why it's a little bit of more of a challenge. Because, well, the punchline is because a weak acid has an equilibrium constant. And so you have to take that into account. So let's work through it. So let's say you have a question that says the initial concentration of an acid is such and such. What is the H plus concentration? So what I'm going to do is I'm going to work through now, or walk you through, a generic Rice equation. Okay, so how is this going to work out? Well, we're going to have Ca as the initial concentration. You're not going to lose 100%. You're going to lose a certain amount X of acid. A certain amount of that is going to decompose. And so your concentration at equilibrium is going to be your initial concentration minus X. What is X? We don't know. That's what we're trying to calculate. Okay. So if HA breaks down, how many H pluses are you going to get for every X that breaks down? Well, you're going to get positive X. And how many A minuses are you going to get? Positive X. So we now know 0 plus X is X, and 0 plus X is X. And now you have, thank goodness, equilibrium concentrations here. At least a representation of those. Right. Okay, so here we go. Let's now look. So Ka is equal to concentration of your reactants. And since one is X and one is X, of your products. And so the numerator is going to be X squared. And this is true every time you have a weak acid for this. And then your starting concentration is going to be Ca minus X. Okay, I'm going to give you, we've discussed these before, but I will go over them, criteria for which you can use the shortcut. But we're going to assume right now that the initial concentration is much, much, much greater than Ka, or we're going to assume that it's much, much, much greater than the hydrogen ion concentration. What that means is this is very large compared to that. So, in the spirit of being being okay to be within only 5% or 10% of the correct value, we're just going to forget this because it's small. So, our equation now reduces to this. Equilibrium constant is equal to x squared divided by Ca. I'm going to rearrange that and come up with this. H plus is now equal to Ca Ka the square root of. This is true for every weak acid for which you're allowed to make the assumption. Let me say that again. This is true for every weak acid that your shortcut criteria are met. If your shortcut criteria are not met, guess what? You have to do the Rice thing and you have to do all of this the long way. So I will tell you a shortcut what I would do. Whether it works or not, I would use the shortcut first because it takes just a second, and I would look on my test, and if I get an answer that's really, really close to the shortcut answer and all the other answers are way, way far apart, then that difference is not going to matter. This tests for a 5% difference. So if the answers on your test vary way more than 5 or 10 or 50 or 100%, then you're going to be close enough to your answer. Now, that's not what we would do in chemistry, but that's what we would do as chemistry majors on a chemistry test. That's part of knowing how to take a test and not so much how to get the exact persnickety correct answer in chemistry. If your answers are very, very close on your multiple choice answers, then this is fails, then you have no choice but to do a very detailed, that is, you have to stick with this equation and solve for the quadratic. Okay, for weak bases, likewise, we could work this same thing out. And of course, now the concentration of hydroxide concentration for any weak base, assuming your shortcut is true, is equal to CbKb square root of. Lovely. Those are shortcuts. Those will save you from having to go through the Rice equation every time. The book, I think, is going to take you through the Rice equation for every stinking equation. Right. So once you derive it, since it's the same, hey, go with it. So I'm going to go back up to page 1 and show you. So we've now covered this and this and this and this. I want to tell you one thing at the bottom. Okay. So there we are. You can test it before the fact. This is a crude rule of thumb, and this is the absolute what you need to do. If Ca divided by Ka is greater than 100, okay, I'm going to rearrange that. If Ca is greater than 100 times Ka, and that is, if Ca is at least 2 orders of magnitude greater than K, this shortcut's probably going to work. At the end of the day, if you don't know Ka and have to work it out, you can always work out using the shortcut and then divide Ca by X and see if it's greater than 20. The version I like to use is I multiply whatever I get times 20 and look to see if my initial concentration is greater than that. So your test for working it is knowing what your initial concentration is and what either your final answer or your equilibrium constant is compared to your initial concentration. Okay, so that's what we want to cover on this segment. On the next segment, we'll come back and we will work a sample problem.